Welcome to class, AP Statistics. This is a voice of a friend whom you have not heard in many, many days. Yes, it is I, Mr. Eicher. I am here, not there, but I am here. You are here. Sounds like an ASB motto. I am here. I should get started though. I'm not sure how long this video is going to be. I am still out sick, as you could guess. I will try to not cough on this video and spread my germs. But here we go. Rather than trying to make a handout about significance tests for the difference of two proportions, I thought I would make a video. So here we go. I guess always good to start a video by changing something. There we go. I think this is our third lesson on section 1. So significance tests. You yesterday did confidence intervals for the difference between two proportions. And you can use confidence intervals to test claims, but those claims would have to be double-sided since a confidence interval has an upper and lower bound. So we need significance tests to test hypotheses, particularly ones that have greater than or less than, since we don't have confidence intervals for that. Well, at least not in our curriculum. So our null hypothesis is, again, in terms of parameters, notice these don't have p-hats, but one proportion, the first proportion minus the second proportion, equals some hypothesized value. The most common hypothesized value is 0, making it very easy. The null hypothesis is that the difference between these two proportions is 0. Again, remember the null hypothesis is assuming that there's no difference with something. So if you're assuming that the proportions haven't changed from one year to the next, then if you subtract them, then theoretically you should get 0 if they're the same, if there's no difference. I like to use this format. You can also see this format. That's if you solve that equation that I just showed you, add p sub 2 to both sides, then you would get the null hypothesis is that the first proportion should equal the second proportion. And remember, the null hypothesis is the hypothesis that we are looking for evidence against the null hypothesis to see if we can conclude the alternative hypothesis. The alternative hypothesis is going to look kind of like it did before. You're going to have a greater than sign. You're going to have a less than sign. Or you're going to have a not equal to sign. I'm not going to try to type that in. So again, the numbers will be the same in the null and alternative hypothesis. And the parameters will be the same. You could also have it like this, if you like to do this kind of thing. Add p sub 2 to both sides. You could also see it written like this, the alternative hypothesis. So in this lesson we'll be practicing writing hypotheses, but ultimately we're trying to get to the whole kit and caboodle of significance tests for the difference in proportions. So read this example, pause the video, and see if you can come up with what the proportions might look like. Sometimes it's helpful with these types of questions. You'll notice you have a lot of numbers around. Sometimes it's helpful just to identify what numbers you have. So this first study had that many individuals, observations. That's n sub 1. The second study had this many individuals. That's n sub 2. The first study had this result. That would be p hat sub 1. The second study had this result. P hat sub 2. So when you're asked to define parameters, parameter would be P1 equals, and it would be the actual percent of teenagers with hearing loss between 1988 and 94. P2, looking right back up here, would be the actual percentage of teenagers who showed some hearing loss from 05 to 06. Notice another key word here is this. Does this data give convincing evidence that hearing loss has increased among teens? That tells you the direction, one-sided, of your significance test. Here's a nice typed out solution for you. Null hypothesis. If you subtract the two percentages of deaf teens, if teenage deafness hasn't increased at all, then you would expect 0. We're looking for evidence that it has increased. Notice this is very dangerous. Notice here, I chose to define P1 as the later year and P2 as the, P1 as the more recent year and P2 as the later year. If you had done P1 as the first study minus P2 as the newer study, if you think that teenage deafness has increased, this would be bigger than this number. So that would actually be a less than 0. So although on the previous slide I said increased would be greater than 0, you have to be very careful how you're subtracting the two. It would become even more evident if you read it like this. If P1 is the earlier study, this is saying teen deafness has actually decreased because in 88 it was bigger than 05. So the moral of the story is be careful how you define the parameters and how important it is to define your parameters in picking the correct inequality sign. So I will summarize again. Both of these answers, this and this, are correct. It all depends on how you define your parameters, if it's like this or if you switch the two. A very important reason why it's important to define your parameters. Please read this example. Pause the video and see if you can write the hypotheses to test. So as I said earlier, sometimes it's helpful to label things. 80 students in school 1, that's N1. 150 in school 2, that's N2. It's really okay that these sample sizes are different. They're both going to be large enough once we check for the normal condition. 19, that's actually X sub 1, number of successes. The success in this case being a child not eating breakfast. Strange to think of success as not eating breakfast. 26 would be X sub 2. P hat 1, therefore, would be 19 over 80. And P hat 2 would be 26 over 150. Notice this number is given when you check the independent condition n is less than or equal to 1/10 of, ooh, that's bad handwriting, big N. State hypotheses. If you haven't stated hypotheses yet, you should pause the video and do that. Remember to define your parameter. So the null hypothesis looks the same as usual. What sign, however, should I use? The key word here is there evidence of a difference between the two schools? We don't know if school 1 or school 2 is better or worse than the other, so we just say, is it different? So we have to put in a not equal to sign. Defining the parameters. I suppose in this case it doesn't matter which one you define as which, since it's not equal to actual proportion. Not really given enough information to say, is this don't eat breakfast regularly, don't eat breakfast on a particular day. But the parameter is the actual proportion of students at the first school who don't eat breakfast something. And then the second proportion is like unto it. Just change this to be the second school. So we want to know if the actual proportion of students who eat breakfast is different between the two. To determine that, we'll do a significance test, but hopefully that's enough practice writing hypotheses. So let's move on to more detailed information. The name of the significance test you may be able to guess. It's called a two-sample z-test, or two-prop z-test on your calculator. One kind of preliminary that we have to talk about that's going to be important for our calculation of the standard deviation of the statistic for the difference between two proportions is called a combined estimate. Because we hypothesize that the proportions of the two samples are equal, that's the null hypothesis, we combine the observed successes to find the combined proportion, which we use p hat sub c. It looks like a complicated formula, but basically all that's happening is you're adding the two sample sizes for a total sample. And you're taking the successes in the one sample, the first school for instance, how many kids in the first school, and then how many kids in the second school didn't have breakfast. And this gives you the combined proportion. We assume the combined proportion p hat is true, just like we assume the null hypothesis parameter is true. And as I said, we use this combined p hat in our standard deviation of the statistic below. Okay, I'm going to go through this quickly. You could always pause this video if you would like to copy something. All this is in the textbook, chapter 10, section 1. But a two-sample z-test for the difference between two proportions. Supposing the random, normal, and independent conditions are met, to test that null hypothesis, first find the combined proportion p hat c of successes, then compute the z statistic. This very complicated formula is not given to you on the formula sheet, but I will remind you that the general formula for a z-score, for instance, is statistic minus parameter divided by standard deviation of statistic. So let's look at this formula. You have your statistic subtracting the two sample proportions. Your parameter very commonly is 0. It doesn't have to be, but it's very common that you're just subtracting 0, which is nice. And this should look similar to the confidence interval standard deviation of the difference between the two proportions. Notice, however, that these have the combined proportion for each of the p-hats. N1 is the first sample, N2 is the second sample. And you are adding. And it gives you a test statistic, a Z-score as it were, a Z statistic. With that, it gives you a Z statistic, which is like right here. And with that Z statistic, you could then find the probability of getting a Z like that, or more extreme. Or if it were double-sided, negative Z would be over here, and you would get that area. But that's what Z gives you. Z allows you then to find a probability that a result that you just got, how likely is that just by random chance? I basically just summarized this. But again, never hurts to reiterate. One-sided greater than, you're finding this area. One-sided less than, this side. Not equal to, is both of those. And again, it's a p-value. P-value is assuming the null hypothesis is true, assuming there's no difference between these two proportions. What's the probability that you would get sample proportions as large or larger as the ones that you got just by random chance? I'll remind you, there are 3 ways to calculate a p-value. Table A, a favorite among many. After, of course, you find your Z-score or Z statistic. Normal CDF. Or you could just find the p-value and a bunch of other stuff if you use 2-prop z-test. 2 for 2 samples, prop for proportion. Z's always goes with proportions, and it's a test, not an interval. And it's under your test menu. And we use this z-test when the conditions are met. Thankfully, the conditions are the same as those for confidence intervals. This isn't always true. In Chapter 9, you may remember that for a confidence interval, you would do n p-hat is greater than or equal to 10 when checking the normal condition. For a significance test, sig t, make sure I'm not putting any cuss words on the board, you would have to do n times your hypothesized proportion. Is that greater than or equal to 10? However, it wouldn't make much sense to do this one with 2 samples now, would it? The difference would be 0, so you could never then be greater than or equal to 10, since your null hypothesis is equal to 0 most of the time. So the conditions, random, normal, independent, like always. I'll just reiterate, just like you read about yesterday. The independent groups condition. When you have 2 groups, you not only have to assume that if this was done properly and there was random selection, that the individuals within the group have independent responses, but also the groups themselves are independent of each other. And we can talk more about that when I return. I wanted you to review this information. If you'd like to pause the video, you can review this. This is all information. Well, the first 2 are from Chapter 9. The last 2 about scope of inference. is from chapter 4. So let's go through the whole process for this question. Pause the video and read this. It should look very familiar to you. So you should already have hypotheses written for this example. You should know how to check conditions from your work with confidence intervals yesterday, but if you'd like to pause this video to check conditions, particularly the normal condition, the random condition, you're told that they were randomly selected teenagers, and it was a similar study, so we take that to mean they randomly selected the other teens in 05 and 06. The independent condition, there are many teens to sample from. We do assume that the teens that were selected in 05 and 06 were not the same teens in 88 and 94, which seems like a fair assumption. Let me show you the solution. Before I show you the solution, how about you try to calculate the combined proportion. I'll write the formula on the screen for you if you didn't get that in your notes. The combined proportion N1 P hat 1, that's the number of successes in the first sample, plus N2 P hat 2, that's the number of successes in the second sample. Success in this case being hearing loss. N1 plus N2 is the total combined sample size. So see if you can calculate the combined proportion and see if you can get a Z statistic. The solution is coming right up. We have our hypotheses. Null hypothesis, alternative hypothesis. You may have used less than 0 if you define your parameters differently. Significance level was stated, 0.05. The name of the test, 2-sample Z test for a difference of proportions. The conditions, random, normal, independent. Notice the normal condition. You have 4 parts, all of them are at least 10. The independent condition, there are many teenagers. Combined proportion, 16.7%. And then the test statistic was 4.05. 4 standard deviations away, seems very, very far away, resulting in a p-value of 0. This p-value tells you, assuming that there's no difference in teen hearing loss between those 2 sets of years, assuming there's no difference, the probability that you would have more teens recently with hearing loss in this random sample is 0. It is incredibly unlikely that you would, just by sampling variability alone, that you would get such a different proportion. Even though your different proportion, notice, is 20%, 19.5% recently, 15% about 20 or 30 years ago. Only a 4% change. But because the sample sizes were so big, even a 4% change gives us evidence. This p-value gives us evidence that hearing loss in teens has indeed increased over that 20-year span from 88 to 05. Part B asked about explanation for this. It asked about Apple. Perhaps it's Apple's fault, and we should bring a lawsuit against Apple because it's their fault that teens have increased hearing loss. Well, before we get to that, we should conclude. Since our p-value 0, basically, is less than that, we reject the null hypothesis. We have convincing evidence that the proportion of all teens with hearing loss has indeed increased between those years. Now, this was a random sample, so we can infer about all teens, not just the teens in this study. However, since it was not an experiment, and it did not have random assignment of subjects to treatments, or treatments to subjects, we cannot infer cause and effect. We cannot say it is Apple's fault. It's possible that teens who listen to iPods are also more likely to listen to music in their cars. Perhaps the car stereo is the cause of hearing loss. So only with experiments can we infer cause and effect, but we can indeed infer cause and effect with experiments. On experiments, we can use these statistical methods for randomized experiments, not just random sampling in surveys. It's much more common in the science field to have randomized experiments and to use this two-sample z-test, or what we'll learn later, two-sample t-test for means in clinical trials and experiments. Now, some may ask, why, when you're sitting at home sick, would you take time to make a video like this? And there are certain examples that are well worth it. Just imagine. Just close your eyes. Go ahead, close your eyes. Don't dream of pizza. Dream of these three things, and then you'll understand my motivation. Duct tape? Liquid nitrogen? Yeah. And warts. I said warts. Those three things. Open your eyes. There was an actual study done about duct tape removing warts. And I've taught you this whole lesson so that you could answer this question about what's better. This is life or death, people. Should you get your wart removed with duct tape treatment? Or should you use the more traditional freezing treatment? Now, I'm shocked that these people didn't use the potato in a bag treatment, which I myself used. But that is too personal of a story to share, especially with a video on YouTube. Read this example. You might want to pause the video, read the example. Maybe have someone read it out loud. Here's your data. It looks like duct tape. It looks like duct tape is a clear winner. The percentage of people, that's about 88% were healed with duct tape, compared to about 60% with liquid nitrogen freezing. However, assuming there was random assignment in this experiment, what if the people who had easier warts to remove just so happened to be randomly assigned to duct tape? Maybe it's not the duct tape. Maybe it's the random assignment. Maybe the people just You know, maybe the really, really bad cases of warts all just so happened, or like a high number just so happened to be in the liquid nitrogen. Should we really blame liquid nitrogen? Maybe, it just got the short end of the stick. So you're going to be performing a significance test to determine if these data suggest that freezing is less successful than duct tape in removing warts at a very small alpha level. Enjoy.